Alright, this thing still doesn't work. I'm still working on it. But I think I might have found something of significance. So here is a logic analyzer recording. And you see how ADS doesn't go low and the transceiver enables and the byte enables change. It's changing in the middle of a clock cycle. When this happens, the active transceiver changes, and perhaps, like, I'm just speculating here, but perhaps um, the transceivers changing during a valid clock cycle is messing with the CPU enough that it doesn't make ADS assert when it's supposed to. And when this happens, it just messes everything up. And hopefully that's the only problem that I'm having. Um, Now, in order to fix this, I actually ran into another problem. The Xilinx XE2C128 CPLD chip that I'm using, it can only do 100 write cycles before it stops working, and I apparently wrote enough data to it that it stops working. So I need to come up with a solution that doesn't use a chip that stops working so soon. So I actually found an FPGA called like a Lattice Ice40, and yeah, on paper it's a lot better and it's a lot faster, and it's 1/3 of the cost, and it loads its program data from a external serial ROM instead of a internal memory bank that breaks really easily. So yeah, now I have to design some system that lets me use a different chip. I'll probably have to make a new motherboard for this one. But I'm going to put the FPGA on a removable card this time, so that way even if that doesn't end up working, I can just make a different one without having to make a whole new motherboard. Here's a schematic for the Ice40 FPGA removable board that I'm making. Um, this one is using a different chip. I was previously using a Xilinx XC2C128. That's a good chip, but the problem is it does not fetch its program data off of an external card. Like, it has to be programmed onto internal memory. And the problem with that is it can only be written to 100 times. Or I think it's up to 100 times. That's what the datasheet says. In my experience, they do not last that long. Like, I think mine stopped working after 27 writes. So that's why I decided to try a different chip. So I have chosen the one of the Ice40 variants in the 144 pin package, and I'm just trying to make a board that will work for that. I was actually able to make my Xilinx one work on the first try. I'm trying to do enough studying that I can get this one working on the first try, but it is going to be more complicated. So this one uses SPI flash to read from, like, it loads the data onto the FPGA from this external memory chip. The advantage of this is that means I just get practically unlimited write cycles. And if the chip ever stops working, I can easily desolder this and just reattach a new one. So this is going to solve my write cycle problems. Okay, the power circuit is pretty much exactly the same as on my Xilinx design. The only difference is that this chip needs a 1.2 volt power input, like for its core, instead of a 1.8 volt. So they conveniently make a 1.2 volt version of the AP7347DQ chip that I was using. So yeah, I just use that. I'm using the same number of surface mount capacitors because that worked when I did it with the Xilinx chip. This one has a lot of inputs. I have around 120 of them connected to slots. So this one, it uses three 40-pin IDE connectors and also a 120-pin PCI slot. So these two connectors, um, they have the same inputs and outputs on each one. I just did this to give me more opportunities for debugging. Um, yeah, it's just going to be easier to debug, see what all the signals are doing. The routing on this was pretty difficult, and I'm still working on it. I'm actually waiting on parts to be delivered so I can make sure that they physically fit this. It's like the one time I didn't wait until I had the parts on hand and just ordered the thing, it turned out one of them was wrong. So I don't order boards until I have all the parts anymore. Yeah, this is kind of more or less what it's going to look like. It's still a work in progress, but this is, I figured out how to get it to route, basically. That's what this is. I am having to do this on a 4-layer board. There's just too much stuff going on to do it on 2 layers. So, yeah, that's pretty much my plan for the FPGA. Hopefully it works. Oh yeah, let me point out one other thing. So over here, yeah, there's this one pin I'm not really 100% sure about. Right here we have VPP 2.5 volts. I don't remember exactly what the documentation says. There is a lot of documentation available for this chip, but it didn't really describe in a way that I could understand what this is for. So what I actually did is I found this. Yeah, this. This is a board that uses a similar FPGA. It's a similar model, but not the exact same. And what they do is this. Yeah, they put a diode on it, and then, yeah, it's 3.3 volts, and then a diode, and then it connects to that. And I don't know what that is. Probably nothing. So basically, I just kind of mindlessly copied that because no, that's probably the best thing to do. So if anybody sees any of mistakes, please leave it in the comments. Yeah, okay, I'm using this for the serial programming. Um, yeah, and then, okay, I'm not sure if the FPGA expects a high or a low reset signal. The schematic says it's active low. I can't remember what the documentation says, but I'm just not taking any risks, so I have a jumper where I can toggle between both possibilities. And if you just see all kinds of random jumpers all around, that's really just what that's for, is just contingency. So basically, if I'm not 100% sure about something, I'll often make a jumper where I can just go between all the possibilities that I think it might be. That usually works out. It works out more often than you'd think. Oh yeah, another thing I wasn't sure about is over here. There's special ground pins for the phase lock loop feature. The documentation says that you're not supposed to connect the PLL grounds to the regular ground, but the problem with that is, like, where else am I supposed to put it, you know? The only other example I have of a schematic that uses this chip doesn't even use the one that has a phase lock loop feature on it. So hopefully this will work if I'm not planning on using phase lock loop features. I mean, I'm not really sure what else I'm supposed to do with it. Okay, here's the schematic to my Arduino shift register debugger. So the problem is that I need to be able to analyze as many signals as possible on my computer while it's running, right? I have an oscilloscope with 4 inputs on it, and then I have a USB logic analyzer with 16 inputs. But if you have a 32-bit data bus and a 32-bit address line and a whole bunch of control signals, that's just not good enough. So I came up with this. It uses shift registers to get more inputs, and then it shifts them in serial onto the general purpose input output on an Arduino. And basically, I'm sacrificing speed for more signals. So this one can handle 94 individual inputs. Actually, I think it's 96. It's either 94 or 96, but it's a lot. I don't expect this to be very fast, but I know that it will at least be able to handle 20 hertz, which is all I really need. This one has a PCI slot on it, and it's also got those same 40-pin IDE headers. So the idea is I would connect this Arduino debugger to that FPGA board, and I can do so either by using a PCI slot or by using 3 IDE cables. And yeah, that way, even if the FPGA card is connected to the computer, I can still connect this debugger to that device using these IDE headers. And then, yeah, okay, routing isn't that difficult for this one. I'm going to do 2 layers and just, it'll probably be good enough. Here's what it's going to look like, more or less. It uses the dual inline pin packages for the shift registers. It's got a PCI slot. Now, once I get this working, and working well, I have 2 different really kernels or operating systems or whatever you want to call it that can run on this system. I have one that runs in real mode, and it can run on pretty much anything 286 class or higher. And then the other one I have is it's written in C++ and it runs in protected mode, which means you need a 386 or a 486 in order to run it. So for the longest time, I thought this real mode operating system was going to be the way to go. But once I figured out how to get linking to work and how to get it to work well, this pretty much became obsolete. But it is really simple, and it takes about 5 kilobytes of storage space to run. One major advantage about this system is that it's great for running on homebrew x86 computers as well as normal x86 computers, because this one doesn't use any BIOS interrupts. It's just, instead of using interrupts that a homebrew computer probably doesn't have, this one just has all of the functionality in the code. I don't really have a whole lot to show because this doesn't do anything, but here's the ATA test. This one doesn't have a file system on it, but it can read ATA drives. I have a hex reader. I mean, that's pretty useful. But yeah, that's my real mode operating system. Okay, so here's the C++ protected mode system booting on a real 486. This is not a modern computer. It has the 486 instruction set and nothing more. Alright, and there you go. So this is modern C++ code. I think it was compiled with like C++ 17, and yeah, it runs surprisingly fast. Now, of course, this computer, it runs at 160 megahertz, so it's not a slow system, but the fact that it's this fast is pretty good, I guess. Let's see, oh yeah, substring test, that's something that should probably be slow. I mean, yeah, that works pretty well. See what happens when I type in CPU info. Okay. See, there you go. It tells me what type of CPU I have. What else do we have? Mem? What does that do? Oh yeah, I got rid of liballoc. That's right. PCI check. Let's see what happens when I do that. This motherboard actually has PCI slots. Okay, I don't think that that's working right, but what else can I do? Okay, yeah, that's pretty much it. That's all the things that this system does. But as you can see, it's surprisingly fast, and yeah. And that's pretty much all I have for today. Thanks for watching. Bye.